Hey guys, what's up? Welcome back to another stream. It has been a very long time. Once again, it's been about a week, but it is New Year's Eve. So, you know what? I guess we'll just pull a 12-hour stream and go straight through the New Year. But today we are going to be doing a second challenge, and today we're going to be looking at the Shunting-Yard algorithm, which is a algorithm that allows you to parse string mathematical expressions in this sort of notation here. So the whole kind of premise of the algorithm is that it looks like this, where if you have a plus b times c minus d, it'll push all the this is why it's called the Shunting-Yard algorithm, because it kind of looks like a shunting train yard. So we have all the variables go across, or numbers, constants go across, and then operators will be pushed down until they are if the operator at the top of the stack is of lower precedence. So like with the plus, there's nothing there, so it just gets pushed down. The multiplication, higher precedence than the plus, so it gets pushed down. With the subtraction, though, the multiplication sign is of higher precedence, so it will get pushed to the output stack, and the subtraction sign will then be pushed to the all the operators that are of greater than or equal precedence will be pushed to the output stack. So that's the multiplication and the addition sign, and then once it's all over, the subtraction sign ends up like that. So I'll give you an example right now. Hold on, let me just... So, this is sort of the algorithm that we will be looking at, but that we'll be implementing. And we're going to do this in JavaScript, because in the future, a project that could be possible would be something like a graphing calculator, which would be pretty fun to do. So with stuff like this, this algorithm does take order of operations into account. So it will do something like this. It won't just do 3 plus 4, 7 times 2, 14 divided by 1 minus 5, etc., etc. So if we have something like this, it'll end up looking like this, and once we get to the evaluation, I'll show you how that we can be able to parse this. And then this also accounts for functions with one or multiple variables, so sine, max, which is pretty cool. So yeah, it'll be pretty interesting to do. I've already done this, so I have some reference code at my side right now just to make sure I don't screw up anything. But yeah, so hopefully this isn't too bad, but we'll see where we get to. All right, so in our YouTube challenges repository, I've created another folder called Shunting-Yard. And because we're doing this in JavaScript, we are going to have to implement this as a web application. So I'm just going to go ahead and create index.html for now. And all index.html is going to do is just call for an input. So I'll just have that Shunting-Yard demonstration. And then in the body, we're just going to have an input. The type is equal to text. I'll call it ID is equal to input. Placeholder is equal to enter expression. Because right now we cannot do full equations, because expressions are things that don't have an equal sign. So you just evaluate one side of that, the entire thing. But equations actually have two sides to an equation, so this will only have one side. So enter expression, and then we'll do a default value of just value is equal to, and I guess we can just copy this one for now, just so we can test to make sure it works. And I'll just make that a slash for division, and that should be all for the input. And then we'll have an input type is equal to submit, ID is equal to btn, and value is equal to evaluate. And then we'll have to have a area to output, so I'll just do a paragraph element, so ID is equal to output, like so, and that should be good enough for, well, that's good for the display. Now we have to add the JavaScript, so we will go ahead and I'm going to create a JavaScript file called main.js, and we have to include that in our index.html. So to do that, just do script source is equal to main.js, and that should be good there. So we can actually just take a look at this in the browser. So I'm just going to copy path, and that's all we need right there. Okay, so that is good. Now we'll start editing our main.js. All right, so let me just grab a sip. I'm a little sick right now, so the water is necessary. I'll have to take a couple breaks to get some more water, but hopefully it's not too bad. Alright, so in main.js, we'll start actually implementing the whatever it is, the algorithm. So we're going to need a couple of functions to start off with. So let me just go through here. So what will happen is we'll have to parse. So the output of this algorithm is called reverse Polish notation, or RPN for short. So that'll be our first step. So I'll define a function called function RPN, and it'll take in the string equation, like so. Oh, what did I just do? And then, where am I going? And then the second function we'll need is a parse. So after we put it into a reverse Polish notation, we'll have to parse it into a tree, so it can be evaluated. We could evaluate it as we put it in reverse Polish notation, but the trick with this is if we parse it into a tree, then we can actually store this equation and use it for something like a graphing calculator, where we can input variables that will have different values, and we don't want to evaluate it immediately. So yeah, that is, and then the last function will be function evaluate, and that will take in a tree. And that's all for now. Okay, so we'll be starting off with the reverse Polish notation, and the first thing we'll need is a queue and a stack. So let q is equal to, the queue is going to be the output, if I'm correct. Let me just make sure. Let me just, yeah, so the queue is going to be the output. So in this photo right here, the output is the queue, and then we're going to have the stack for the operator. So let stack is equal to operator. And in JavaScript, it's cool because lists and arrays are like stacks. So we can call pop, we can call push, we can do all that stuff. And then in this algorithm, we'll have to go through, nope, not that. We're going to have to go through each. So the first thing is, while there are tokens to read a token. So this looks like something like a for loop. So we'll do for var I is equal to 0. We'll have to get the length of the equation. So eqlen is equal to eqn.length. I is less than eqlen I++. So we'll just be going through each token And to denote the token, we'll do let t for token is equal to eqni. All right. So this will be good because now we can actually just look at this token and go through it. But the problem is, what happens if we have some like sign where the token is actually 3 characters or a multi-character number? So we'll have to account for that later on. But for now, we'll just have to know that this algorithm just skips all commas and all spaces. So once we get the t, we can just say if t is equal to a space or t is equal to a comma, just continue, because we can't do anything with that. Alright, so now we'll have to determine the type. So in each loop, we'll have to have an object. So the object is equal to nothing. So the object will be what we, so if we have t as this token, what we'll have to do is we'll have to get the object as sign. So if t is s in here, we have to get the object as sign. So object will be the current thing, that operator, function, or number that we're working with, and then let type is equal to nothing for now too, because the type will determine what we do with the actual object. Alright, so left, so to determine what the object will be, we'll have to go through a little bit of a algorithm, and we'll need a couple of functions first. We'll actually need a couple of functions and lists to be honest, because this is gonna get a little lengthy. But all right, so for now, all I'm gonna do is I'm just gonna go through all the constants and all the functions that we will need and will use. Sorry. Oh, shit. All the functions and all the constants that we will use, and I'll just put them in a list now, just so we don't have to create that stuff later. All right. So the first thing we'll need is constants. So let constants is equal to a dictionary, and we'll just be using pi and e for now. So pi maps to math.pi, and e maps to math.e. All right. And the math library is a native JavaScript library, so that's all good there. And then we'll need constant names. So let constant names is equal to object.keys constants. This is how you get the list of the keys. In JavaScript, you just do object.keys, and then you pass in a dictionary, so that will return pi and e in strings. We'll need this just to know if the object is actually a constant. So, and then next we'll need functions. So there's something called unary functions and binary functions. So unary functions take in one input, so that's going to be stuff like the tangent, arctangent, stuff like that. And then the binary functions will be functions that take in 2 inputs, so your basic for operations, plus, minus, and then also stuff like the max that we saw over here, because max takes 2 inputs. And then, so what we'll have to do is, hold on, we're actually going to need another function before this, because the way I created this earlier was I created a function that allowed me to generate a class or a dictionary where there were different properties that were set for each function. So I'm going to create a function at the top called function generate function. So genfunc, and it's going to take in evaluate. So the eval will be a callback to some function that will evaluate the function given the parameters. So eval, then type, we'll leave that for now, and then which is precision, or sorry, not precision, precedence, will be equal to 0 for the base, and then left associative is equal to true. So most functions that need it will be left associative. So only function that this matters for is the sorry. The only functions that associativity matters for is the for operators and the exponent, but the exponent side is right associative, because you do the I don't know why, but it's don't ask me about it. I'm not a math genius, so but it will matter here. So left associative is going to generally be set to true, and all this will do is return a dictionary where eval is eval, t becomes type, a precedence is just prec, and then left is left, so like that. And if we create bodies like this, then it'll be easier to parse through the function once we go into the evaluation function. So for the type, we'll actually need to denote a couple of type variables up here, because that'll be necessary for this and for the reverse Polish notation parse. So we'll have 6 different types. So let type op for operator just equal O for now. Let type const for constants and variables just be C. Let type func equal to F. Let type else, so this is if it's not found, and it'll throw an error, so E. Let type left parenthesis is equal to just the left parenthesis for now. Parenthesis, not parenthesis, parenthesis, and then let type r paren be the right parenthesis, like so. And then the general type will be type func, just because that'll be the easiest when we initialize our dictionary functions. So now we will actually get into looking at the unary functions and the binary functions. So this is going to be kind of annoying to do. You don't have to do all these. I will. Because, I like to go into depth, but also when we create a graphing calculator, a lot of these functions will be necessary, especially in advanced math courses where you do use all these functions. So unary functions are going to be stuff like the log functions, the trig functions. So let's just do that right now. So let unary functions equal to, and for now, I'm just going to type all this out. So sine goes to gen func. We're going to be calling the function, that function, and the eval will just point to a lambda function that takes an x as a parameter, and it'll just return math.sine of x. And that's it. So the reason why this function right here is very convenient is because we only have to pass in an eval. But for most of these functions, the type will be function, so we don't have to pass in anything there. We don't have to do anything extra there. The precedence will be 0. It'll take precedence over other stuff. Left will be, and it's left associative. So, well, the associativity doesn't matter here. So we don't want to have to just say true and not know what it means. So the only thing that needs to be specified for each of these functions will just be the actual evaluation of those functions. So now we're going to do cosine. I'll just go through all these. I'm actually just going to do like 6, and then I'll paste in the ones later. So math.cos x, and I'll paste in the rest of them later but they don't really matter. And then tan becomes gen func x, and that returns math.tan x. And then the last 2 will be ln, log, and square root. So ln becomes gen func x, and that just returns math.ln of x. And then log returns gen func, or goes to gen func, and then lambda x becomes math dot log 10, just for basic. X. Oh, you know what? ln is actually not a thing. This has to be math.log. And the math.log is just actually goes to the natural logarithm, so base e. And then the last thing we'll do is just square root. So squirt becomes gen func, pass an x, and return math dot squirt of x, like so. So that's a couple of unary functions, and now we'll do all of the binary functions, which is 8, I believe. All right, so let binary functions equal to a dictionary, and so we'll start off with the plus, and that'll map to gen func, and we'll pass an x, y. So now you see that we're doing 2 parameters. That's why it's in the binary functions dictionary, and we'll have to specify which one later on in the evaluation. So it'll just return x plus y. The type is now type operator, and the precedence is 2 here. I think I misspoke earlier when I set the default precedence to 0. When evaluating these functions, the precedence doesn't matter, so 0 is just a placeholder there just to make sure it evaluates it properly. Okay, so we'll do minus, so the gen func will pass an x and y as lambda parameters, and that'll just do x minus y. And we will do type op again, and that'll have the same precedence too. Multiplication, that'll be gen func, x, y, goes to x times y, and we'll do type op, and gets a precedence of 3 because it's higher precedence. And then the division, we gen func x, xy, returns x divided by y, type op, and it'll be 3 as well. And then we have the modulus operator. You don't have to do this if you don't want to. I'm just putting it here just because. So modulus xy returns x modulo y, type op, and it has the same precedence as multiplication and division. And then the power, so that's just going to be the caret, and it'll be gen func xy goes to x, or math.pow xy, and it'll be type operator. This is of higher precedence than any of the others, so 4th, remember your PEMDAS boys, simple algebra. And then this one is not going to be left associative, so left associativity will be false. And then I'm going to do max and min. You don't have to do these, but I'm just going to do them now just so we can have the ability to test the Wikipedia demo. So max, gen func, x and y goes to math dot max of x and y. Don't have to do specify anything else. And then min goes to gen func x, xy, and goes to math.min xy, and that's all there. So the reason why, so with here, because we have a default of left to true, we don't have to specify that parameter for any of these other functions, which is why, since we only have to do it for that one function, it's pretty convenient not to have to type in true, true, true every time. So yeah, I just used a bunch of these defaults here, just where they were most common, so we don't have to type them in every single time. All right, so those are the binary functions, and now we have to, similarly to the constant names, we have to get function names. So let functions is equal to object.keys, and we'll do the unary functions, and then we'll do .concat. That's how you add 2 lists together in JavaScript. So .concat and object.keys and binary functions. I need to remove that space. All right, So that's functions, and then we'll need let operators is equal to plus, minus, times, divided, modulo, and power. So the reason why I'm doing this as a string is just because we'll need it, because we need to treat these ones separately than the others, because these are technically not functions, these are operators. But I'm just putting them here just so the evaluation is easier. Alright, so let operators do that, and then let left brackets, so you can actually have a variety in what brackets you use. So let left brackets is equal to the open parentheses, open curly brace, and then open square brackets, and then let right brackets equal to right parenthesis, right curly brace, and the right square bracket. Whatever one you use doesn't matter. This is just to identify the type. They'll all be converted to parentheses once we start parsing. All right. So that is all of the variables that we'll need for now. And now we'll need a couple of identification functions that allow us to identify the type of a token. So we'll have to do function is number, and that'll take in just C. We'll do function get the numerical value, so numval of C. Function is variable C. Function is function. That's kind of confusing to say. C, and then function find element I, EQ, and list. And this will be just to allow us to get sign from S. So we'll be going through each element. So in find element, we'll just be going through each of these keys here and seeing if that is equal to the string at that location right there. And then we'll need two more, get precedence. So function get precedence operator, just so we don't have to type in binary functions at that dot prec. We can just do get precedence of the operator, and then function is left associative of op. So we'll start from the bottom and we'll go up. Alright, so return. So for left associative, it'll just be a return binary functions at op dot left, because we'll only be doing the binary functions. Oh, actually, it might not. I think that's okay, but just to be safe, we'll do if object dot keys in binary functions dot includes op. So if it is the operators binary functions dictionary, we'll just do return binary functions at op dot left, and otherwise we'll just return true, because default is true, because this function has default of left associativity. And then for get precedence, it'll be something similar. So if object dot keys add binary functions dot includes op, we'll do return binary functions at op dot prec, and otherwise just return 0, because that is the default value. Oh, I'm sorry. I'm actually gonna go get water right now, so I'll see you guys in 5 seconds. Okay, I'm back. Alright, so we just did get precedence, and now we have to do the find element function. So the way this will work is we will have to go through each element in the list that is specified here, and that'll either be the... Sorry. Give me a second. That'll either be the unary functions or binary functions, whichever one there. And we'll just go through each key and see if it... Well, actually, I think we will be going through the operator names, the function names here. And we'll see where it is and if it matches, etc. Alright, so for var j is equal to 0, len is equal to list.length, j is less than len, and j++. And what we'll do is we'll say var n is equal to list at j.length. So this will be the length of the function name. So for min it would be 3, max it would be 3. These would be 3. For ln it would be 2, squirt it would be 4, etc. So the length there, and then if the equation, a substring from I to I plus n, so if we're at the ith character and we want to go 3 over to see if it's min, we'll just get the substring from, well actually, if it's like this equation here, and we're at this index, and we're looking at the max function, we'll start here, and we'll go 1, 2, 3 over, and we'll compare it to C, if that's the function. So if the substring is equal to the list at j, then or actually, let's just... Oh, no, never mind. We can't do that. So, if the list at j, we're just going to return an array of values. So, we will return true to indicate that it's been found. We'll return the actual function, list at j, and then we'll return the length of that function, so n. Sorry, one more. Okay, I should be good now. Alright, sorry about that again. Alright, so yeah, this array is just a convenient way to return several values. And now, we will do, otherwise we'll just return that it was not found, an empty operator, and 1. You'll see why the 1 is there in a second. So next, what we're going to want to do is we'll do the is function. So this will just be a simple return functions that includes C. For variable, it'll be something similar. So, well, actually, do we have variables? Variables is not necessary here. This will be necessary if we do implement this in the graphing calculator. So I'll just leave that there for now. So get numval. We'll do if type of C is a number, so you get the type of something in JavaScript. So if it's a number, just return the value, just return C. Else if constant names dot includes C. Shit, I hate being sick so much. So if constant names include C, just return constants at C. So if we passed in pi, it would return the value of pi. Speaking of, I'm going to go on a tangent here. Get it? Fuck. Get it? Tangent? Isn't that really funny? Wait, where is it? Guys, get it? Tangent? That's really funny, isn't it? I just screwed my freaking computer up. What is the value of pi? Value of pi. That really nice. Thank you, DuckDuckGo. 100,000 digits. There you go. Nice. You think I can find my social security number? You know what, guys? Just post your social security numbers in chat, and I can actually just look them up, see if I can find them. Post them, please. Please put them in chat. Hold on. Hold on. What does this mean? Bit rate. Is this recording? It looks like, yeah. Alright. More info. It says excellent connection. What the fuck? What the fuck? Alright, I'm not gonna care right now. You think I can find my social security number? Let's see if we can find it. 1, 2, 3, 4, 5, 6. Can't. Guess what the last 3 digits of my social security are? Find digits in pi. 1, 2, 3, 4, 5, 6, 7, 8, 9. You could not find my social? God damn it. But I do want a pi shower curtain. How old is this site? God damn. 3194, okay. How old is this? Doesn't say about pi. Oh shit. I don't. This looks very old. Share on Twitter. Yeah, this is nice site. All right, let's continue. All right, last thing. Or actually, in getNumVal, we just need to say else. Just return the parsed number value. So parse float of c, like that. And then the last function is number. Will just be if type of c is equal to number, return true. Else, just return if it's not is nan c. So if it's not doesn't exist, or if it's in constant names, dot includes c, or if c is equal to a decimal place or a period, because this will be necessary if we do decimal places or decimals in our calculations. Alright, so that's all the necessary functions that we'll need for this pretty much the entire algorithm. So now we can actually get into the parsing. So after we have determined that the token is not a space or a comma, we want to see if it's a number. So if is number, and we'll pass in t. So that'll once again call the function, this function right here, test it, blah blah blah. You get the deal. So if it is, we'll set the type is equal to type const. We'll set the object equal to t, and now we'll have to figure out where. Well, hold on. Do I know what I'm doing here? Hold on. Okay, so I'm just looking at my code and I don't know what I wrote, but I think I get the gist. So we want to find, so if we have something like pi, where we have this big ass string and we want to parse it, we don't want to just get 9 and 4 separately. We want to get 9, 4, 7, 7, 7, blah, 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 blah. So we want to keep going. We want to keep going through the equation until the token we find is not a number. So if I is less than the equation length -1, so if it's before the end of the string, we want to do while is number eqn at I plus 1, and we'll do object plus equals eqn at I plus 1 and I plus plus, and if I is greater than or equal to eq len -1, break. You could honestly probably hold on. Shit. Fuck. Oh my god. This is the worst time to be sick ever. Oh god, I'm dying. Oh shit. I'm trying to get the tissue out of my box, but that stupid thing got stuck. Oh, 1 second. Alright, so once we have added all the tokens to it, remember t is, all these are still a string, so we just have to get the number value. So object is equal to get numVal of object. And JavaScript, once again, is great because the types are dynamic, so we can convert this from string to number within the same I don't fucking know. I don't know. Within the same stupid thing. Whatever it is. Within the same variable. I'm losing my mind right now. Okay. Alright, so next is variable. We can leave that for later. So if it's not a number, we want to get if it's an expression, if it's a function or an operator. Alright, so let data equal to find element from I using the equation, and we'll pass in functions. So, oh no, why did I do that? So what this does is it passes in I, the index, the equation, which we're looking at right now, and the function. So data will be this, the array that it returns. So let found equal to data at 0. Object is equal to data at 1, because that is what the function it found is. And then let n equal to data at 2. So that's just the length of the function. So if it's found, we want to figure out if it's going to be an operator or a function, because functions includes all of the functions, so sine, cosine, etc., but also all of the operators, plus, minus, all those. So we want to determine if it's a function or an operator. So if operators dot includes object type is equal to type op. We can actually make this a ternary operator. So type is equal to operators dot includes object question mark true type op, false type func. Yeah, so that's just a little ternary operator right there. And if it's not found, we want to see if it's a constant. So we're going to do the same thing. So data is equal to find element I eqn, and then constant names. God, why do I keep doing that? Found is equal to data at 0. Object is equal to data at 1. And n is equal to data at 2. And if found, so if it did find a constant, it will just do type is equal to type at type const. And if it wasn't found, we have several possibilities. So it could be a parenthesis, or it could be something that we don't know. So we'll have to determine that. So if left brackets dot includes t, type is equal to type at L paren. So this gives you the freedom to use any of these brackets as a bracket. It doesn't really matter which one you use. Otherwise, else if right brackets dot includes t, type is equal to type at R paren, like so. And otherwise, just say that the type is equal to type else. So we did not find anything that matched the token. So now, what we will do is we're going to actually go through the token. So now that we've determined what the token is, we need to determine what to do with the token. Alright, so I'll just put a comment here. Determine what token is. Hold on. Get. Okay, so alright, so now we're going to determine what to do with the token. So do something with token. I almost forgot also. We have to append or add n to I, because if we found a function that is 3 characters long, we want to go 3 characters down. We don't want to stay and then, so if we got max, we want to get max, return max, put it in there, whatever. But we don't want to go to AX next, because that's going to throw an error. So we just want to put the cursor 3 characters across to the end of max, like that. Alright, so do something with token. So now what we will do is we're going to have to do something with a switch. So we'll have to, I'm going to create a variable called last stack, the last element in the stack, because it'll be necessary to do this. So stack at stack.length -1. And we'll do switch type, and we'll just go through each type here. So first one we'll do is just constant, so type const. And if you guys remember, not that, this. So if it's a constant, push it to the output queue. So case type const q dot push. It's object. And then you have to remember to break your cases. The next one is case type func. We'll do stack.push, just because for any functions you just push it, because it's going to have a lower precedence than operator, so it doesn't matter. Just go ahead and break. Well, actually, just look at this here. So if it's a token, just push it to the stack, like so. Next case is going to be operator, so type op. And now this is going to be a little annoying to do. So we'll actually just break it for now, and then we'll take care of that in a second, and we'll just define all the cases, and then we'll look into that implementation. So case, next one is light left parenthesis, so L paren, and we're just going to push it to the stack, so stack.push, and it'll be just that. Break, the R paren, so right parenthesis. This is also somewhat annoying, so we'll just break it for now. And then default, we will just return null, just to signify that we found something that was not what we intended to have. Okay, so type op, we want to do this. All right, so if stack.length is not equal to 0. So if there's stuff in the stack, and if there's not stuff in the stack, we just want to throw the operator onto the stack. So stack.push operator and break. But we will be pushing the operator to the stack at the end no matter what, so that'll just stay there. So if there is stuff on the stack, we want to do this. I'm actually going to have to disable a couple of extensions because I ran into this problem a while ago with prettier formatting, and I'm going to disable it right now because they were annoying me. Alright, so disable, and then I got to reload my thing. So file, Command-Shift-P, I'm just going to reload window. Alright. Alright, so if it's an operator and there is stuff in the stack, we want to do this. So we're essentially going to go while there is a function at the top of the stack, or there is another operator at the top of the stack with greater precedence, or if it has equal precedence and is left associative, and it's not a left parenthesis. And if that is true, we just want to pop operators to the stack, from the stack to the queue. Alright, so that's going to look like this. So while, I'm just going to break that for now, and I'm just going to do the conditions in a second, and I'll just do this body for now. So it'll just be queue.push stack.pop. So stack.pop removes the last item but also returns it. So that's essentially what we want to do there. And then if stack.length is equal to 0, we just want to break because there's nothing left. I mistyped there. And we just want to update the last stack variable. It's equal to stack at stack.length -1, just because we can't keep it as the same thing all the time. So the reason why I created this variable in the first place was just so we didn't have to type this whole thing out in these conditions, which will get a little annoying. So first condition, if, and then we're going to do in parentheses, or while functions dot includes last stack and it's not an operator, includes last stack. So what this does is while it's a function or an operator, or while it's a function and not an operator. So this is good because we just want to pop all the functions up top. What if we run into them at the top of the stack? That's not in this description, but this this doesn't implement functions in unary operators, stuff like that. So it'll be or, and then next we'll do get precedence of the last stack, and if it's greater than, get precedence of object, or get precedence of last stack is equal to get precedence of object, and and is left associative last stack. I'll go back to the code in a second, to this in a second, but let me just finish writing this out. And is not a left bracket. not left brackets dot includes last stack, like that. Okay, so let's go through this side by side with this code right here. All right, so first thing we do, I can do a little bit of this, a little bit of that. All right, so this first line here, this was not in the macro or the pseudocode, but this is something I ran into in testing, so I just added that line there. While get precedence, so while there is an operator at the top of the queue with a greater top of the stack with greater precedence. So if get precedence of the last item in the stack is greater than get precedence of the object, or the operator has the same precedence and is left associative. So equal precedence and is left associative, last stack, and so all of this is the hold on, did I write this properly? I don't think I wrote this properly. I think it's supposed to be like this. Okay, yeah. So, or if get precedence is equal and left associative, and so this whole thing has to be true, and it's not a left bracket. And if this passes, then do this whole body right here. So we can get rid of that, and open that back up. All right. So that is if it's an operator. Now we want to deal if it's a right parenthesis. All right. So if it is a right parenthesis, we want to do a while last stack does not equal to a left parenthesis, and we don't have to do the test to see if stack.length is if it has anything, because with right parenthesis it will have stuff, and if it doesn't, it'll run into an error, and that will be the user's fault. All right, so q.push, and it'll be stack.pop, so the whole thing there. So what this does is this right here. So while the operator at the top is not a left parenthesis, I'll just pop the operator to the output queue, and then we know that the top is now going to be a left parenthesis, so we'll just pop it. So actually we'll just do, hold on, and then we have to update last stack. Hold on, last stack is equal to stack at stack.length -1. All right, and then we'll just do stack.pop because we know it's going to be a left parenthesis, and then break. So that is our large for loop. So this is our going for, so for each token. So for each token, we have to determine what it is, and then we have to do something with that token based on its type. All right, so once we have parsed every token, we want to pop everything to the queue. So while stack.length is greater than 0, we just want to say q.push stack.pop. We just want to put everything back onto the queue as it says here. So no more tokens. While there's still more tokens on the stack, then we just want to pop them to the queue. And then we want to return the queue. Okay. So now we're going to want to test this. All right. So how did I think I had it in. All right. So we can implement this at the bottom. So we'll do document.query selector, and it'll be hashtag button for, because remember we're looking for this button, and we want to do add event listener, and it'll just be the click, and we'll just pass an E there. And we'll do let eqn is equal to in element, or no, not document.query selector. We'll do it is input dot value, not node value, dot value. No, what? What the hell? All right, dot value, and then we're gonna actually parse that. So let rpn is equal to rpn of the equation, and then document.query selector, the output, we're just gonna set that to the rpn dot inner is equal to rpn. Dot, hold on, or no, it's just, we'll just do a space dot join rpn. So we want to join each element, because remember the queue is a list, so we're returning a list from the function, so we just want to join it with each thing with a space. So let's go into, so if we have this function right here, so let's just reload this. We have this function here. We should get that. So let's just check. Uh-oh. Something's wrong. Console. Op is not defined. 180. Stack.push, not op. obj. Now it should work. Evaluate. Dot join. Huh. How do you, oh, I think that's a Python function. What am I doing? rpn.join. Yeah, it's the opposite in Python. The string is used to join the list, but here I guess it's different. Alright, evaluate. Fuck. Null. What? Hold on. Console.log. Hold on. No, what? What the fuck? Uh-oh. Alright, this is gonna be good. This is gonna be great. Alright. Okay, so console.log, or no. I wanna do console.log object q, how do you yeah, q and then stack. Alright, so I'm gonna take this, drag it over here. Alright. Okay. So let's reload, evaluate. Okay, so let's look at this. So 3 gives us 3, 4. Yeah, that's fine. And a plus. That's good. 3, 4 plus, right? 3, 4. What is this? 3, 4. What the fuck is going on? 3, 4. What? Hold on. 3 plus 4. Let me see if this works. 3, 4. 3, 4 plus, that works. Why is it null? I want to see something. constant operator, constant else. Is the space? Oh, because it's I didn't freaking. Oh, you know why? Because I left the X in there for the multiplication. Else still though. Is that not? I guess that's not. Oh, that's not a subtraction sign. Okay, that works now. Okay. Yeah, that's just. I copied and pasted. You know, that's why you never copy and paste, boys. Never copy and paste. Never. Fuck. No. Still no? Oh, because the stupid bitch. Oh, I need to reset the value. Alright, 3 plus 4 times the asterisk and then minus as a dash, not a EM dash. Don't be alright, value it. I hope this is right. Alright, so 342, good, times, good, 1 5, good, minus, good, 2 3, good, up, or caret, divided by plus. Let's go! That is good. Alright, so we have, in the first hour and 7 minutes, we have accomplished, that's the algorithm. That is the actual algorithm. Now we just have to parse it. So that was the putting the infix notation, as they call it, into reverse Polish notation. Or I mean, I guess we can just try with this as well. So it's going to be. Hold on. Let me just make sure that this works as well. All right. So sign max. Make sure it's divide by. And then times pi. Alright, evaluate. No, fuck. Oh, because it's the pi. Yeah. Don't worry, guys. It's okay. There we go. 2, 3, max, 3, divide by. Good. Yeah. Alright, that's good. Okay. So now we have to figure out how to parse this thing into a tree. So I'm going to go into OneNote for this, and I'm going to take out my drawing tablet, old classic drawing tablet. Okay, I'm getting it out, and here it is. Alright, so I am just going to go ahead and copy this onto here, and I'm going to show you guys how we want to. Alright, so it's 2, 3, max, 3, divide by, pi, times, sine. Hold on, shunting. Okay. So if this is our reverse Polish notation, the way we're going to parse this is, so we're going to go through and we're going to add numbers to a stack. So what we're going to have is a stack. Hold on. So the way our end goal is going to be this. So we want to have 2, 3. It's going to be. Here, yeah, I'm just going to demonstrate it in smaller trees and then I'll add them together. So we're going to find the two numbers. So we're going to go from left to right. So 2, 3. So our stack is going to look like this. So stack. We're going to have 2 and then 2, 3. And then what we're going to have is, hold on. All right. So we have our element. And then the stack. So we have 2, stack looks like 2. 3, stack is 2, 3 because that's just a number. And then now we have max. So with each function, if it's a unary function, it'll take the last number. If it's a binary function, it'll take the last 2. So what this does is it takes the last 2, so we create a tree. Max is the node. And this points has a left of 2 and a right of 3. Okay? So now we can call this A. Alright, element 3. So now the, oh, hold on. Let me just drag this. I never actually lasso select. Alright, let's drag that over there. And then pen. Alright, so now the stack is empty because we've cleared out we popped the last 2 numbers. So next is 3. So the stack looks like 3. Actually, the stack looks like this. The stack is going to be A, because this will be a number once we evaluate it. So the stack will be A, and now it's A3. And hold on, let me just, I don't know why the circle didn't go. Alright, so the next number is, or the next element is division. So we're going to have a B here, and it'll be divide. It'll be A and 3. So the stack will just be B. Next will be pi, and that's a number, so it'll be B comma pi. And then multiplication. So the multiply, we're going to have another tree, C, and it'll be multiply, and it'll be B and pi, and the stack will just be C. And then the last one is sine, but because sine is a unary operator, it only requires 1 operator, so I'll call it D, and sine is the root node, and D, and it'll just have a left value of C. So what is this going to look like in the general tree? So the final tree, so D, and then the last statement of the evaluate function will just be return the stack.pop. So this final tree, when we evaluate it, it's going to look like this. So we have a sine at the top, left hand of C. So C is a multiplication with a right hand of pi and a left hand of B, which is a division of A and 3. So 3 on the right, and A is a max of 2 and 3. Alright, so that is how we're going to parse, sorry for my handwriting, but that is the final goal of our tree. And the way that we'll evaluate this is we'll essentially we'll have a recursive function that just goes iteratively and just evaluates each hand, and then so for example with max it would evaluate 2, which is 2, it'll evaluate 3, and then it'll pass in 2 and 3 to max. So yeah, so essentially this is what we're going to be doing. So let me just put the drawing tablet away so we can get into this. Okay, so I'll leave that up for now. I can actually just minimize, hold on. So if you guys want to pause this video now and just look at that, you can do that, but sorry for my handwriting again. So let's go back to the code. Alright, so what we're going to do now, so I'm just going to, I'll comment this out, or I'll actually let the thing print out RPN. That doesn't really matter for now. Alright, so let me, alright, so let's get into the parse method. So we want to do, we'll have a stack. So let stack equal to an empty array for now. So for each element in the RPN, so array dot from RPN dot for each, and each token we want to do, we're going to have a node structure. So we'll have to actually create another function that is similar to the genfunc function, but it's going to be called gen node. So function gen node, and it'll pass in val func is equal to true, so the default will be a function, and unary will be true. So I'm just choosing these default functions or default values. That's just what's the most common, and the most common thing is a function, and its most common is unary. Well, it will be most common will be unary once we get past once we add more trig functions and all that stuff. All right, so gen node will just be returning a dictionary. So val is just val. That can be a callback, and if it's a function, it will be a callback. Func is going to be func. Unary is going to be unary. Right is null for now. The right child and the left child will both be null, and then the name will just be an empty string, and that'll be just gen node. And then in parse, what we're going to want to do is we're going to have I'm just going to say let tr equal to null. So this is going to be like the tree. And we'll have to determine, once again, what each token is. So if is number t, we just want to push it to the stack. So tr is equal to gen node. Well, actually, we don't want to push it to the stack yet. We'll be doing that at the end. But we want to generate a node for the token, and it's not going to be a function, so we'll just pass in t and false as the node. All right, and then if it's a variable, well, we don't know variables yet, but we will. That can be next video or something. And else we can do. So we're gonna have to distinguish now between binary and unary functions. So once again, that's just going to vary between how many different parameters from the stack that they take. So else, it's going to look like, hold on, we'll do this. So if object.keys binary functions dot includes t, we want to do tr is equal to gen node and binary functions at t, and it'll be true. It's going to be a function, but it's not going to be a unary function. I think I actually said that true is the most common here with gen node. It's not. Most of them are not unary, but it's just there just because it doesn't really matter, but it's that doesn't really matter there, but it's fine. Alright, so we'll need a and b, which will be the last two since it's a binary function. So the last two from the stack. So let a equal to stack.pop, let b equal to stack.pop. So now we'll have to generate a tree node for each of the last elements, unless it's not, only if it's not a tree already. So for here, where did it go? What is going on? What is going on? Oh, there we go. But still, what the fuck? Okay, what is going on? Okay. So, for example, here, A is in the stack, A3 in the stack, so we won't generate another tree for A because A is already a tree, it is already a node. So we'll only have to generate a new node for 3 in this case. Alright, so we'll do if type of A is equal to number. We'll have to do tr.write is equal to gen node A false. And the reason why we're doing write is because here 2 and 3, or let's get a better example. With the division, we want to do A divided by 3. So we're going to do left divided by right. So because 3 is at the top of the stack, we want to do 3 as a dividend and A is the divisor. So A divided by 3. And A is the second to last element there. All right, so tr.right is like that, and then otherwise tr.left is equal to b. All right. Wait, no. Wait, no, hold on. So if the type of A is a number, we want to generate a new node for it. Otherwise, we just want to pass. We just want to say that's the right child, and then we'll do the same thing for B. So if type of B is equal to number, tr.left is equal to gen node, it'll be B, and then it's not going to be a function. And otherwise, we just want to do tr.left is equal to B. And that's for the binary. And now for unary, else if object.keys unary functions dot includes t tr is equal to gen node unary functions at t. And it is a function, and it is not, and it is unary, so we don't have to pass in any other parameters because the default is true and true, which applies for this. All right, so tr is that, and we just need the last element. So a is equal to stack.pop, and then we'll do the same thing. So if type of a is equal to number, tr.left is equal to gen node a false because it's not a function, and otherwise we just want to say tr.left is equal to a because that's already a tree, and that is that. And then for every iteration we just want to push the so stack.push tr, and we also want to set the name of the node. So so tr.name is equal to t, but that doesn't really matter for now. Alright, so that is essentially that. And then the last thing we'll do is just return stack.pop. Like so. And now we'll do the evaluation. We can test this all together because this is kind of hard to debug. It's kind of annoying, but we can if we run into errors, but it's kind of annoying to do because we'll have to. Because you can't like print out it. You can't print this out, really. It'll be kind of hard to look at. All right, so eval. So pass in the tree, and we'll look at this. So if tree.func. So if the node is a function, we want to do if tree.unary. We just want to do return tree.val.eval. Eval is a function in this node in the value because it's a function. And then we'll just do eval. It's going to be recursive tree.left. So evaluate the left-hand side and pass it into the right. So with this, it's just going to evaluate the whole thing here and then pass it into side, and then it'll recursively do the same. So otherwise, if it's not unary, we want to do return tree.val.eval, evaluate the left hand, and then evaluate the right hand. And once again, this is binary. This is a binary function, so it will pass in two parameters: left first and then right. The left, that order does matter. And if it's not a function, we just want to do so if constant names dot includes tree dot val. We just want to return the constant value at tree dot val. Otherwise, if no, and otherwise just return the. So if it's a constant, just return the value of the constant. Otherwise, just return the value because it's going to be a number. Okay, so. And now let val equal to evaluate RPN. Or no. We need to convert this to a tree first. So we have RPN. So let tree equal to parse RPN, and then the value will be evaluate the tree. and then we can console.log RPN, console.log tree, and console.log val. And the inner HTML will just be val. Okay, so now let's look at our test. So for this one, evaluate that. Let's test this. So let's actually do the let's test this. Okay, so what we have is, let me get back the drawing tablet, and I actually need the hands to drag this down. So what's the function? Let me just type this in, because I have a calculator at my side, so I'm just going to type this in. So 3 plus 4 times 2 divided by, in parentheses, 1 minus 5, up 2, up 3. Alright, so let's look. So we have 3 plus 4 times 2 divided by 1 minus 5 up 2 up 3. So this will become in like, as if anyone else were to write it, it would become 3 plus 4 times, no, I can't write, times 2 divided by 1 minus 5 to 2 to 3, like that. Alright, and this will evaluate to 3.0001, which is that. Nice. Alright, so that works out well. And now we can test out the other one. So let's get this one. So this one is going to be sine of, hold on, max 2 comma 3 divided by 3 times pi. And the way this will look is we'll have sine of max of 2 comma 3 divided by 3 times pi, and this will essentially look like that. So it'll just be sine of pi over 3 times the max of 2, 3. And that should evaluate to 0, right? Because the maximum of 2 and 3 is 1, or the maximum of 2 and 3 is 3. 3 divided by 3 is 1. So this will become sine of pi 3 over 3. That cancels, so sine of pi is 0. And we're in radians right now. So let's actually just type this out. Alright, so we have sine of max of 2 comma 3 divided by 3 times pi, or we got to type out pi, and this should give us, shit, this is no good. Something went wrong here. Source. Let me just hold on. Let me just set the default value to that, just so we can. So it's sine of max 2 comma 3, and it's divided by 3 times pi. Let me just get this out of the way. Okay. Alright, so let's see. Alright, so let's reload this. And I'm going to go into my Chrome debugger and I'm going to set some breakpoints. Actually, what is... going on? All right. Shit. Let me just set a breakpoint at all of these right here. Right, evaluate. All right. So equation. All right, equation is equal to that. That's good. All right, RPN crashes. Paused on breakpoint, but where? Yeah. Okay, something went wrong. I'm assuming. Did you know what I think I did? What is wrong? Let's do a little bit of this. T type. All right. Let me just reload. Let's go ahead and evaluate. Console S. Function, constant. Oh shit. Constant. Right parenthesis, and then it broke. Is it not looking at the left parenthesis? That might be the. One second. That might be the problem. Now that should be. Hold on. Let me just put these together. See what's going on. Let's get rid of these breakpoints right now. Console.log, and I want to do T type. All right, SM. Wait, hold on. It's not giving me the right parenthesis. Hold on. All right, while. Shit. SM2, comma. Why is it? Oh, it's not reading left parentheses. So there has to be something with I plus equals N. Is it I plus? Oh, it's I plus equals N minus 1. I'm really stupid. I had that in my test and I did not. I neglected to read that. Okay, so this should work now. There we go. That number, which times 10 to the negative 16th, that's 0. Good. We did it. We did it. Now let's do some crazy function. And let's do like a little bit of tangent. Or actually, let's just add an error catch just in case we're stupid. So if RPN is equal to null, otherwise do all this shit. Like that. Actually, we can make this so let var is equal to invalid input. if RPN hold on. I'm just going to do a little bit of error catching on the user's part. So if RPN is null, we did something wrong, blah, 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 blah. Yeah, that works. Okay, so just reload this, make sure that works. Invalid input. What do you mean invalid input? Oh, because I scope. Make sure, yeah. Fuck. Alright, that's good. Now let's do something a little bit, okay. So, let's do a little, can I try this? Do I have a graphing calculator? No, I have a graphing calculator on here. Hold on. Don't I? I guess I don't. Oh, I don't have it on this computer. All right, whatever. I'll just put it on my calculator myself. Okay, so let's do a bit of tangent of cosine of 3 ln 5 divided by 6 times pi. Let me just make sure I'm doing this. Alright, so what I wrote was tangent of cosine of 3 times ln of 5 divided by 6 times pi, like that, and then evaluate, and it works. Alright, it is working. That is good. That is very, very good. Alright, I think that has been a successful, how long? Hour and 38-minute stream. It's been, we actually got a lot done. We did this entire thing. Next video might start implementing this into a graphing calculator. So that's the reason why I actually put this into a tree in the first place, because it's going to be a lot easier to store equations in tree and in parsed form, so that if you want to plug in a variable, you just plug it in and it treats it like a number. So that's why the tree is useful. But so yeah, this will be pretty cool to see how this will work. I actually have a demo. I did. What is it? File. No, it's not that. It's C source programming web /equations/index.html. So this is what the graphing calculator. This is what I have in store right now. It's on a canvas. If I were to do like 3 times x, we graph 3 times x and do a little bit of this. So this is what we have in store right now. Stay tuned, because it might come later this week. Happy New Year, or Happy New Year's Eve, and Happy New Year in what is that? 8 hours? No, not 8 hours. 10 hours. And I bid you all farewell. I've become Shakespeare. So yeah, I will see you guys whenever I go back online. It might be later this week, possibly later this week, because I have not been keeping it on my schedule very well. And yeah, I will see you guys then. See you. I said see you 4 times. Goodbye.